So we're in the physics lab, and this is my best partner in the world, Caroline. She can introduce herself in sign language. Oh, there you go. That was amazing. So at this class, I'll learn how to juggle. That's the thing.
Within 20 hours.
Within 20 hours. Hello everyone. Today I'm going to discuss physics of juggling. Last year I watched a very interesting video. It was a TED Talk and a speaker, Josh Kaufman, raised a question that intrigued me. The question was,
how long does it take to acquire a new skill?
He refers to a professor of psychology at Florida State University, K. Anders Ericsson, who is internationally recognized as a researcher in the psychological nature of expertise on human performance. Professor's research explains that on average, person needs
10,000 hours. Anybody ever heard this? 10,000. It takes 10,000 hours. If you want to learn something new, if you want to be good at it, it's going to take 10,000 hours to get there. And I read this in book after book and website after website, and my mental experience of reading all of this stuff was like, no!
10,000 hours is a lot of time, and it's an equivalent of 5 years of full-time job. But here where it gets interesting. 10,000 hours rule comes out of the studies of expert level performance. Professor Ericsson studied world-class athletes, musicians, and chess grandmasters. So 10,000 hours is the time required to get to the top of competitive field. You basically have to be Michael Phelps. So how much time do we really need to acquire a new skill like juggling and be relatively good at it? Well,
20 hours. That's it. You can go from knowing nothing about any skill that you can think of. Want to learn a language? Want to learn how to draw? Want to learn how to juggle flaming chainsaws? If you put 20 hours of focused, deliberate practice into that thing, you will be astounded.
And he proves his point by learning how to play ukulele.
Just a small town girl.
what I wanted is to check 20-hour rule by learning how to juggle 3 balls by using physics as an essential tool for reaching my goal. Also, I'm hoping to understand how juggling works from physics perspective. What's the biomechanical aspects to it? How balls are moving in the air, and how should I throw them in order to keep the momentum?
I did find some information online about the subject. For example, about the timing of throws, different ways of juggling, and about this incredible guy who can juggle 14 balls at once. But I didn't find anything helpful until I saw these guys, who introduced me to Claude Shannon's equation, which I found very interesting. But I'll talk about it way later.
I'm Tara.
I think this video will be helpful for people that are trying to better understand physics, learn how to juggle, and are interested how juggling is working from biomechanical perspective. Juggling is quite complex process. The physics of it includes parabolic arcs, speed, velocity, acceleration, air resistance, and force of gravity. During the experiment, I'll be looking at the elbow joint as the system of interest, muscles that provide force for rotation, trajectory of balls, and of course a weight shift. My hypothesis is that with tools that knowledge of physics provides, I'll be able to learn how to juggle in 10 hours instead of 20.
To collect data, I'm using Pascal Capstone software and sensors like video sensor, force plates, and goniometers. They will allow me to create graphs and extrapolate data from them. But first, let's talk about the representation of the magnitude and direction of forces. To do that, we use vectors. Magnitude is expressed by a numerical value. Direction can be represented in a variety of ways. We use quantitative, which is with coordinates or angles. So we'll analyze the movement as two-dimensional. Basically, we'll have x and y system of coordinate. For position, velocity, we have x and y, and acceleration, also x and y. So now let's see what my predictions will look like. So let's make 6 segments here. For the position, let's start with y. Let's make a first segment. This is when the arm is holding the ball before the throw, and last segment is when the arm is holding the ball after catching it. So, in my opinion, this is how it's going to look like. So here will be a moment of stillness, and then in y direction, it will go up, graph, and down. So I think the peak is going to be somewhere here. It's going to be the turnaround point. In x direction, I think there will be no changes. It'll be just like a little bit constant, basically, because I'm not expecting it to move a lot. What's about acceleration in y direction? I think, well, of course, here it's going to be still, and then we're going to have peak here, and I think it'll be kind of constant here, and then it will go down, and again it will be constant, and here it's going to be 0. Acceleration in x direction, I think it's going to look constant pretty much close to 0, and here will be a period of stillness. And velocity in y direction, well, I expect it to be 0 here, and then I expect to maximum velocity be at this point, and then go down, and the maximum velocity will be at this point, and I'll go back here. So whenever acceleration is 0, the velocity will be max. Velocity in x direction, I don't expect much changes here either. It will probably go up here, it will probably go down here, and it's going to be right here. So this is my predictions for a linear world. Basically, I'm just going to track a ball, so the system of interest in this case is just a ball when it's flying up and landing back in my hand. My prediction for angular world will look like this. So we have position, velocity, and acceleration again. I'll break this down to 6 segments again, and I will start with position now. So I don't think it's gonna start with 0. It's gonna go a little bit farther, and it will have 2 peaks like these. And yeah, now acceleration. So it'll start from the 0, and it will have peak up and peak down, peak up and peak down. And now it's easier to predict velocity. I think that whenever, well, there's a rule, whenever acceleration is touching 0, velocity is max. So this represents a full cycle of a ball going from one hand to another and then coming back to the hand. So that's my predictions. Yo, John, you gotta catch it.
He's doing a lacrosse face-off right now.
Let's go!
Now we're gonna take a look at the raw data. As you can see, I'm only tracking the ball, so this is the linear kinematics, and this is how the graph looks like. We can also look at it in more detail. You can see that in my predictions I missed this little segment right here in the beginning. And that's when the arm goes down before the throw. Well, I'll break this down into segments. So this is the first segment of stillness, and the second segment will be speeding up, going down. That's the segment that I missed. So third segment is slowing down but still going down, and the next segment is speeding up, going up, and I'm putting it at the max velocity where the acceleration is 0, as we can see. And then this segment is where the ball is in the air basically, and at this point I'm catching it, so the velocity is again max, and this represents going down, slowing down. Let me find this spot. Yeah, right here. And this segment is going up, speeding up again, because I'm completing the full cycle. We can see the max velocity and max acceleration to 0. Again, ball is in the air the entire time, and again this is probably where I'm catching the ball. So let's put letters on each segment: A, B, C, D, E, F, G, and H. So let's go all over it again. So A segment we don't basically need because it's a segment of stillness. Let's not talk about it. Segment B is when we going down, speeding up. As we can see, the acceleration is max at this point, where velocity, where acceleration is at the 0. Then movement is still going down, but we are slowing down, as we can see from the position graph. Then we are going up, speeding up with the max velocity at 1.74 meters per second. So this ball is in the air over here, so the only force that's acting on the ball is the force of gravity. We can see it from the velocity that it's constantly going down, and the acceleration at this point is going down too. Then here we have going down, slowing down, still with an arm after catching, and at this segment we're going up, speeding up with the maximum velocity of 1.93, exactly where the acceleration is 0. So this is the turnaround point in the segment E and segment H. About X position, we can see that's kinda, well, moving from right to left or left to right. I think it's more left to right. And we can see that velocities are kind of the same spots where the velocity peaks of Y. So it means that my segments are right. So these are segments that I have, and let's do some calculations now. So now we have all the segments ready, and we know what's going on. So the relation between velocity and acceleration is simple. So when two vectors are pointing in the same direction, speeding up, and if they're pointing in the opposite direction, the object is slowing down. So what's going on in our segment? So segment A, nothing's going on basically. That's the period of stillness. In segment B, velocity in y direction going down, speeding up, and velocity in next direction is constant. In segment C, in y direction is slowing down, and x direction again constant. In segment D, object is speeding up in y direction and going up, and also it looks like it's speeding up and moving to the right in x direction. Segment E, the object is in the free fall and only influenced by force of gravity, and for the purpose of this experiment I'm not considering the air resistance. So the object is slowing down, turns around, this is the around point, and then going down, speeding up. I also can make two segments right here to represent it, but yeah, I won't. In x-axis, the object is moving right with constant speed. F segment tells us that the object is still going down, slowing down, and constant in the x dimension. We can see that numbers are pretty small right here. In G segment, ball is speeding up, going up, and speeding up, going left. And in H, we see that ball is in the air. Everything from the segment E applies here as well. And in segment I, ball is slowing down, and this is the end of our motion. Now I'm going to find a resultant angle. It's basically a combination of two vectors, in our case velocity x and y, so we'll know the combination of both velocities. This is how I'm going to do this. So I pick a point. It's most interesting in my opinion. Let it be here, where velocity y is max. So we have 1.74 for y and 0.1 meters per second for x. So the formula to find the resultant vector is square root of vx squared plus vy squared. So we plug in numbers, and we have 3.003, so basically we have 3. Also we can calculate the direction of vector, so we have formula for that too. So this is the formula. We just have to divide, and we plug in numbers. So our angle is 3.308 degrees. So, and we can see it from this image. So this is right at the point that I picked. So we can see this angle is basically has 3 degrees. So at this point at maximum velocity. Here I drew force diagrams for each segment. They're displaying the force vectors representing the direction and relative sizes of forces acting on my system, in this case the ball. Green arrow indicates force of gravity, which is the same at all times. Blue is a normal force, and pink is representing the force of hand. Now let's find the total force that's acting on the ball. We all know Newton's second law that describes the relationship between an object's mass and the amount of force needed to calculate it. Force equals mass times acceleration. The force can be a single force, or it can be the combination of more than one force. In my case, I'll pick 2 points on acceleration graph and will calculate the total force acting on the ball. I'll pick point at y, so total force at y will equal mass times acceleration at y. And x, so the total force in x will equal mass times acceleration in x. I know that the weight of a ball is 100 grams, which is 0.1 kilogram, which gives us 1 Newton. Now I can write the formula and plug in numbers. So total force in y equals to mass times acceleration in y, which gives us hand force in y direction plus weight equals to mass times acceleration in y direction. And this gives us a force of the hand equals mass times acceleration in y direction plus weight. So let's plug in numbers. And we have 1.917 newtons. Now we can find out the hand force to weight ratio, which is 1.917 divided by 1 gives us 19.917. Now let's calculate total forces in x direction. So we take the same point as for y direction. Total force in x direction equals to mass times acceleration in mass direction. Hand force equals m times acceleration in x direction plus weight. Then hand force in x direction equals 0.1 kilograms times 0.5 meters per second squared plus 1 newton. And hand force in x direction is 1.05 newtons. So the ratio is 1.05 divided by 1 will be still 1.05. Here's the graphical representation of the calculations that I just did. So red arrow is the force of the hand in y direction, yellow is the force of the hand in x direction, blue is the weight force, and black is the total force of the hand. The second point that I'm picking is over here, where acceleration in y direction is 10.09 meters per second squared and acceleration in x direction is 0.91 meters per second squared. These are the calculations. Feel free to pause the video. And here's a graphical representation of magnitude of forces that are acting on the ball at this point. Red arrow is the hand force in y direction, yellow arrow is the hand force in x direction, blue arrow represents the weight, and black is the total of hand force. Here I have the position graph, kinetic energy graph, and the total net force graph in x direction. From looking at it, we can determine the segments at which the object is going or losing energy and moving. So this is the first segment. We have gain in kinetic energy in x direction. The force is pretty much moving in the same direction, and the object is moving to the right. Now at this segment, we can see that we have also lost of kinetic energy, and total net force is moving in the opposite direction, but position wise the ball is still moving to the right. In this segment we can see that everything is constant, nothing is going on, and in these two segments we see the same thing as in the first two segments, with only change in the direction of the segment, of the movement. Now I'm going to analyze relation between position, total net force, and kinetic energy in y direction. This looks much more interesting than x direction. So this first segment will be here, where we have gain in kinetic energy, total force is going up, and the object is moving up. Here we have loss in kinetic energy, net force, but the ball is still going up. Nothing is happening pretty much at this segment, it's a turnaround point. Now the object is going down, gains kinetic energy and net force. In this segment the object is still going down, but loses kinetic energy and net force. Here object remains pretty much still, and the cycle starts again with these segments. This is the relation, and now we can move on to the total kinetic energy. Now I have another graph which gives me information about change in kinetic energy in x and y directions, and also the total change in kinetic energy. We can see again where exactly a lot of force is generated. Also, it's obvious how small is kinetic energy volume of x in comparison to y. X is red here and y is represented as blue. Now I will calculate how much power is generated during the throw. So I'm basically finding the rate at which work is done. So power is a unit of work or energy transferred over time. In our case, we have total kinetic energy, so the formula is pretty simple. So power equals change in kinetic energy total over change in time. So I take this point right before the ball leaves hand, where total kinetic energy is 0.22 joules, and pick another point where this peak starts exactly, and I plug in the numbers into the formula. So we have 0.22 joules over 1.668 minus 1.235 seconds, and it gives us 0.5 joules per second, which is half of the watt. This is the net force over time graph. Here I'm showing the average net force in y direction by looking at the mean of the slope, which gives me 0.28 newtons. Also, by looking at the area under the under the slope, gives us the change in momentum, which in this case is 0.2 newtons second, which is the same as kilograms meters per second. Here we see that power goes up, and also I picked the same spot segment in x direction, because the data is very jiggly and it's hard to pick a good slope in x direction. We see that average net force here is 0.03 newtons, and change in momentum is only also 0.3 newtons seconds. And the power in this area goes to the right. Let's look at the raw data in angular world. So here we have me juggling with goniometers on. This is what it looks like. And also from the side. Now let's break this down by segments. We have a position graph again, angular velocity and angular acceleration. I already have segments ready, so I just need to find out what is going on here. Our system of interest is elbow, and muscle that provide movement are biceps and triceps. So what we're going to look at is which muscle is dominating at which point. In first segment we have angular velocity going up and also this nice peak in acceleration, so it means we have deflection in this segment. So biceps is dominating. Here we have extension, so the triceps is dominating. Again, we can see velocity is going down, acceleration has this nice peak going down. Again, biceps is dominating in this fragment. And again biceps, and I'm sorry, triceps, and so on. I took screenshots for just the first two segments, so we can now look deeper into the picture. So for the segment A, we have the picture where biceps is dominating. We have also two forces here besides biceps. It's weight of the ball and weight of the forearm. I'll talk about it more detail in a minute. Now let's take a look at the segment B. We can see that triceps is dominating here. I'll represent it with an arrow and add both forces. Now I will find muscle forces. According to my data, flexion at this point reaches maximum acceleration. So biceps is dominating. Also we have two forces here, and joint, elbow, and I prepared already all the information. So I have angular acceleration, which is 8 rads per second squared, moment of inertia from the special table. I have weight of the ball in newtons. I have perpendicular to the ball, so it goes from the axis, from the joint to the force, but it has to be perpendicular to it. I have a weight of the forearm, also calculated from the special table, and are perpendicular to the forearm, and of course are perpendicular to the muscle. So now I have everything that I need to calculate muscle force. So the formula is total torque equals moment of inertia time acceleration, and we have muscle torque, weight of the forearm torque, and weight of the ball torque, that equals to inertia times acceleration. And we know that torque is force times r perpendicular, so we can derive this formula now. So we have this formula, and we just solving for force of the muscle. So we have the formula which states that force of the muscle equals to moment of inertia times acceleration plus force of the weight of the forearm times r perpendicular plus force of weight of the ball times r perpendicular, and all this over r perpendicular to the muscle. So now we just plug in numbers and solve. So we have 138.25 kilograms. Wow, I'm strong. So this is the force that biceps generates. Oh, I'm sorry, it's 138.25 newtons. To convert it to kilograms, I have to divide this number by 9.81, and now we have kilograms, so it's going to be 14 kilograms. I made a mistake. Now I will find the force of triceps. At this point of maximum acceleration, we see flexion, so our triceps is dominating, so we're going to calculate how much. Our numbers are the same, only the acceleration is different and are perpendicular to the muscle. We have some forces acting on our system of interest, but here we have different direction. So same forces, different direction. Unlike in biceps where torque went this way, in this case for torque it's going the other way. So we'll see the formula will look a little different. So now let's solve for it. So total torque equals to moment of inertia times acceleration. So we have this relationship right here, and I'm just gonna derive it quickly and plug in numbers so I don't waste time and the video is not too long. So we have 173.2 newtons, which is approximately 17.6 kilograms. I also decided to find out how many calories I spent during single throw. So I took data from 3 sources, this, and this. I found that for one throw I spent 1 joule. So let's assume that I make 1000 throws a day, which is about the 12 minutes of juggling. So it means that I spent 1000 joules, which is 2.38 calories. If we divide it and convert it to food calories, this is what we have. If I also take into consideration weight shift, we can see from the force plates how much force I generate. It means that after juggling for 10 minutes, I easily deserve a candy. And finally, Shannon's Claude juggling theorem. So it's basically an equation. So it's F plus D times H equals to V plus D times N, where F is the time a ball spends in the air, D is the time a ball spends in the hand, V is the time a hand spends empty without the ball, and N is the number of balls, H is the number of hands. And depending on how balanced this equation is after plugging in numbers, that determines how good of the juggler I am. So let's give it a try. So let's plug in numbers. So I have 2.9 equals 3.24. So as you can see, it's pretty close, but still my juggling is not good enough and balanced enough to increase the number of balls. So the gentleman who invented this theorem was a famous mathematician, and also he was an accomplished juggler, so I kind of trust him.
So not only I know how to juggle now, I also can do some tricks. Like this one. So I'm not sure if it's physics that helped me to learn how to juggle, or juggling that helped me to learn physics. But this is what I got, and sorry that this video is so long.